The purpose of this video is to work out some of the examples on the 2.6 notes that we did not do in class. Solving systems of linear equations by substitution and elimination is an Algebra 1 topic, so I didn't work all the examples in class, but for those of you that would like a little extra help, we're going to work out the rest of the examples on this video. So let's go ahead and take a look at example number 2. We're going to solve the system of equations in example number 2 using the substitution method. All right, so if you take a look at these two equations, when you do the substitution method, you want to solve one of the two equations for either x or y. Well, if you look at this first equation, it looks like it would be very simple. We could solve this equation for y in just one step. So I'm going to go ahead and rewrite that first equation and solve it for y. So we have 3x is equal to y minus 4. All right, so if I'm solving for y, we can do that in one step. Since 4 is being subtracted from y, to undo that, we will add 4 to both sides. And we will, I keep hoping will get better with writing with this air slate. Okay, we get 3x plus 4 is equal to y. All right, so we've taken the first equation and we have solved it for y. So now what we're going to do is look at the second equation and see this y right here. What we're going to do is replace y with what it's equal to. Right here it says that y is equal to 3x plus 4. So we're just going to go back and rewrite that second equation, but we're going to make a substitution. That's why it's called the substitution method. Where I see a y, I'm not going to write y. I'm instead going to write the expression 3x plus 4. So let's rewrite this second equation from left to right. We would have 5x is equal to, now instead of y, I'm going to write what it's equal to. I'm going to write 3x plus 4. And then don't stop there. I'm rewriting this entire equation. So I've written the 5x, the equals. I've replaced y with 3x plus 4, but I still have to rewrite plus 2. All right, so when we do that, now take a look at this equation. You can see we just have one variable, and that's x. We don't have two different variables anymore. So we can solve this equation for x. I am going to real quick simplify the right side by combining like terms. We'd have 3x plus 6. Now I'm going to subtract 3x from both sides because I only want one x on one side of the equal sign. I get 2x is equal to 6, and then divide both sides by 2. X is equal to 3. Now, you might feel finished, but we're not done yet. Remember, we are trying to find the ordered pair, the xy ordered pair that satisfies both of these equations at the same time. We've only found half of it. We have only found the x. So now to find y, I can go back to any of these equations. I can use this equation. I can use this equation. This might be a good choice because it's already solved for y. As long as I haven't made an error in this first step, I can certainly take my x, plug it in right here, and find out what y is. So instead of 3x plus 4, I'm going to write 3 times 3 plus 4, and then do the arithmetic. 3 times 3 is 9, plus 4 is 13, so y is 13. All right, so we have found our x and y value. The last thing we're going to do is just write our solution as an ordered pair, because remember, graphically, we have just found the coordinates of the point where these two lines intersect, and those coordinates would be 3, 13. Remember, this is called an ordered pair for a reason, because we put them in order. The first value will always be an x value. The second value will always be a y value. All right, now we're going to work example number 4, again using the substitution method. So what I want to do is take either of these equations and solve them for either x or y. It doesn't matter which equation you choose. It doesn't matter which variable you solve for, so just pick something easy. I'm looking at this first equation. It looks like it would be very simple to solve that for y with just one step. So I'm going to take this first equation and rewrite it right here. We have 3x plus y is equal to 3. Now I want to solve it for y. I want to get the y by itself. Since 3x is being added to it, we're going to subtract 3x from both sides. And we will get y on the left is equal to, now I can write the right side, I can write it 3, these are unlike terms that cannot be combined, so I can either write it 3 minus 3x, or I kind of prefer to put it in mx plus b form, so I'm going to put the x term first. It is negative, so I would write 3x plus 3. All right, so I took the first equation and I solved it for y. So now I'm going to look at that second equation and see where y is right here. I'm just going to rewrite this equation, except instead of writing a y right here, I'm going to write what y is equal to, which is negative 3x plus 3. All right, so rewriting the second equation, instead of 2 plus y, we're going to write 2 plus what y is equal to. Oops, you know what? Since I'm adding a negative 3x, I'm going to change that, and oops, that's not what I'm going to do. Hold on. There we go. I'm going to erase that, and instead of writing 2 plus, since I'm adding a negative 3x, the simplest way to write that would be 2 minus 3x. Sorry about all this stuff. Oh. All right, so I'm going to write 2 minus 3x plus 3. Okay, so again, we're rewriting this equation. Instead of 2 plus y, we wrote 2 plus negative 3x plus 3, and that's all equal to negative 3x. All right, now, whenever you can, simplify. I see some constant terms here that can be combined. So I would get 5 minus 3x is equal to negative 3x. Now, at this point, I have a variable on both sides. I want to eliminate one or the other. So I might think, okay, I want to get rid of this negative 3x. Let's add 3x to both sides. And when we do, something interesting is going to happen. Okay, on the left side, we get 5. On the right side, negative 3x plus 3x is 0. Now, those two things are not equal to each other. Okay, so look what happened. The variables dropped out completely, and we have an untrue statement. So what in the world does that mean? All right, well, if I go back to my original equation, or the original two equations, I'm going to find the slope of both of those. And let's do that. So using our little formula we have to find slope, I'm going to find slope of the first equation by taking the opposite of a over b. And when I do that, I get, let's see, a is 3, so the opposite of 3 would be negative 3. Okay, b is 1, so I get negative 3 for the slope of the first line. Okay, the slope of the second line, again, I'm going to take the opposite of a over b. Oh, you know what? This is not in standard form. Okay, so maybe instead, let's solve it for y real quick. If I subtract 2 from both sides, I would have y is equal to negative 3x minus 2. All right, let me just review what I just did because I didn't write it down. I'm just subtracting 2 from both sides. Since I got that quickly into slope-intercept form, I can see that the slope again is negative 3. So we have two lines that have the same slope. Okay, so if two lines have the same slope, they're either parallel or they're coinciding. To determine what's going on here, we also need to look at their y-intercepts. Well, the second equation, since it's already in slope-intercept form, I can see that its y-intercept is negative 2. The first equation that's in standard form, I'm going to take c over b to find its y-intercept. So that would be 3 over 1. And 3 over 1 is equal to 3. So notice we have two lines that have the same slope but different y-intercepts. So what does that mean? That means the two lines are parallel. And remember, if two lines are parallel, that means they're never going to intersect. Okay, they're never going to have a, oops, sorry, it's supposed to be parallel. Okay, we're never going to have a point that lies on both lines at the same time. That's why algebraically you ended up with a statement like this that makes no sense. So if you're solving a system of equations, if the variables drop out and you get a statement that is not true ever, you know you're looking at parallel lines, and therefore we'll say that there is no solution. So no solution, oh sorry, is your final answer. All right, no solution.